the neuroaffective junction. Then we're going to look at what happens at the neuromuscular junction. And it's very similar. The only thing is that the neuroaffective junction is in the autonomic nervous system. Right, so that means the postganglionic neuron innervating the affected organ. At the neuromuscular junction is going to be your motor neuron, which in this case is only going to be one neuron. I'm going to split into the way it works for the autonomic nervous system. And that is going to innervate your voluntary cells. So let's see what we know about the neuromuscular junction so far. So how many skeletal muscle fibers does a single motor neuron typically innervate? So one motor neuron, how many muscle fibers would that innervate? That would be an important point. So that actually innervates many fibers. So one motor neuron is going to split off into several axon terminals, which innervate more than one muscle fiber. Okay? So we're going to see that a single muscle fiber can only be innervated by one neuron. And I'm going to explain that as we go on. So our first objective is to understand the functional anatomy of the somatic nervous system, specifically what happens at the nerve. Now, let's go really groundwork here. The anatomy of the somatic nervous system is that it contains a motor neuron. As I mentioned before, it differs from the autonomic nervous system because we don't have that preganglionic, postganglionic setup that we did in the autonomic nervous system. We have one motor neuron. It's going to arise from the ventral horn of the spinal cord. Again, I'm going to contrast it to the autonomic nervous system where the fibers arose from the lateral horn. Right? These fibers are arising from the ventral horn. They're going to exit the spinal cord on the ventral root. They're going to enter a spinal nerve, and they're going to go all the way and innervate a piece of muscle, voluntary muscle. Not cardiac, not smooth. Okay? The neurotransmitter here is only going to be one. It's just acetylcholine. So it's not going to be what we saw in the autonomic nervous system. But again, I'm going to keep contrasting those so you can see the differences. And then the receptors are always going to be nicotinic. If you remember, we described two types of cholinergic receptors. One was muscarinic, that was found on the affected tissue. And one was nicotinic, which is found on the postganglionic neuron. Here we only have one receptor type, that's nicotinic cholinergic. Right, so the fibers arise from the ventral horn. They innervate voluntary skeletal muscle. The only neurotransmitter here is acetylcholine, and the only receptor here is a nicotinic cholinergic receptor. Now, when you look at the neuromuscular junction, we have what's called a motor unit. In the somatic nervous system, there's a motor unit. And that's going to comprise of a motor neuron and the muscle fibers that it's innervated. Okay, so a single motor neuron, such as one of these, one is in blue, that's motor neuron 1. But you can see it ends off in several different axon terminals. And then we innervate different fibers. So that goes back to that question you saw at first. One motor neuron, for example, let's take 2, is going to have several fibers innervating more than one muscle. Several axon terminals, innervating more than one muscle fiber. And I know we haven't looked at the anatomy of muscle yet, but many muscle fibers make up a muscle barrier. Okay, we're going to get to that when we look at muscle physiology. Now, contrasting that, when we look at a single muscle fiber, so if you take just one of these, it can only be innervated by one motor neuron. Okay? So one neuron, many fibers, one fiber can only be innervated by one neuron. So let's see what happens at the neuromuscular junction, which is that place where a motor neuron meets skeletal muscle tissue. And we're going to start by looking at the motor neuron side. So what's going on at that neuron? First of all, whether or not that neuron is excited, whether or not that's going to have an action potential generated is going to depend on a phenomenon called summation. I think you have studied this already. That's going to be the addition of the excitatory postsynaptic potentials and any inhibitory postsynaptic potentials. And if the excitatory postsynaptic potentials are more, they're more dominating, we're going to have an action potential being generated in this neuron. It's going to propagate down the length of that axon. And in the case, let's say there were more inhibitory postsynaptic potentials here, we would not reach threshold. We would not have an action potential propagating down this axis. Okay. Now, when an action potential is propagated, right, we have enough excitatory postsynaptic potential to activate an action potential. This is going to trigger it right down the length of that neuron. Right? And it's going to trigger the release of acetylcholine from that axon terminal. Now, when acetylcholine is released from the axon terminal, we're going to generate what's called an end plate potential. So an end plate potential is specifically what we call the action potential at the neuromuscular junction. It's called an end plate potential. Nothing fancy. It's the same action potential we've been seeing, just that when it occurs at the neuromuscular junction, it's called an end plate potential. And why? Because it usually has enough force to excite muscle contraction. Now, when you look on the muscle side, we saw what happened with that motor neuron, an action potential was generated, it propagated down the length of the axon, acetylcholine is released from that axon terminal, and it's going to propagate an end plate potential. On the motor side is called the motor end plate. The motor end plate. And that's where the terminal bouton, terminal axon of that motor neuron meets with the muscle tissue. The terminal axon, motor end plate. Okay. And just to recap here, all motor neurons release acetylcholine. All the receptors on the motor end plate are always nicotinic, right? And there's also the presence of this enzyme called acetylcholinesterase. Acetylcholinesterase. And that enzyme is going to linger at the neuromuscular junction and eat up any excess acetylcholine. And that's going to terminate muscle contraction. Because if you have the presence of acetylcholine at the neuromuscular junction, it will continue to excite that muscle tissue. It will continue to contract. So that's the purpose of this enzyme. And we'll see how that functions in a minute. Now, when that acetylcholine crosses the neuromuscular junction, it's going to bind to a nicotinic receptor. And just to remind ourselves, a nicotinic receptor is an ionotropic receptor, meaning that this ligand, which is a neurotransmitter, will bind onto this receptor, which is also acting as a channel. It's going to open up and it's going to allow sodium to rush in, more so than potassium is rushing out, and that is going to excite that muscle tissue and generate an potential, which allows the muscle to contract. Everyone still with me? Any questions so far? Okay. So let's see specifically the steps of what happens at the neuromuscular junction. Again, this is going to be the most important thing in this lecture, so not very much. All right. So we have our motor neuron, our terminal bouton. Okay, this is your motor neuron. Again, the fibers here are rising from the ventral horn of the spinal cord. And then we have our motor end plate. So this is your motor end plate. So I'm going to write here motor neuron and motor end plate. And again, this is skeletal muscle. So this is voluntary. Now within the terminal Buton, we have some vesicles. And there's only one type of neurotransmitter here. I'm going to keep reiterating that. Only acetylcholine. Okay. Now on this side, we're going to have a nicotinic cholinergic receptor. So I'll write nicotinic cholinergic receptor. Okay. Now an action potential, again, depending on the summation of excitatory postsynaptic potentials and inhibitory postsynaptic potentials, let's say the excitatory was dominant, we had an action potential being generated here. It's going to propagate along this axon, and when it gets to the terminal Buton, it is going to trigger the opening of voltage-gated calcium channels. And that is going to cause calcium to rush into this terminal Buton. Okay. The rushing in of calcium makes inside of here more positive, and that triggers exocytosis. Okay, this is something, again, very similar to what we saw at the neuroeffector junction. Exocytosis occurs, and these neurotransmitter vesicles are released into the neuromuscular junction. The vesicle is going to fuse with the membrane of the Buton, and the contents are released into the neuromuscular junction. They're going to go and bind to this nicotinic cholinergic receptor. And because this receptor also acts as a channel, that's going to trigger the opening up of this channel. And when that happens, again, sodium is going to rush in more so than potassium rushes out. Okay. And that is going to depolarize this membrane. And the depolarization of this membrane is going to trigger an end plate potential. An end plate potential. Okay, remember this is the motor end plate. And that's going to allow the muscle to contract. Okay, I'll just write here end plate potential. Okay. Now, when the muscle is done contracting, you're still going to have some acetylcholine lingering at this neuromuscular junction. Let me label this the neuromuscular junction. Okay. So what's going to happen? There's an enzyme called acetylcholinesterase. Acetylcholinesterase here, and it's going to go and sort of chomp, it's going to act like a little Pac-Man, and chomp these excess acetylcholine into two. Okay. It's going to spit out acetate. Can you guys still see that? It's going to spit out acetate, and it's going to spit back into the terminal Buton choline. Right? So this acetylcholinesterase is going to cut this molecule into acetate, which can diffuse away, and choline, which is reuptaken into the terminal Buton to be recycled to make more acetylcholine. And that's how we're going to clear away the neuromuscular junction and cease muscle contraction.